Good afternoon, dear friends. My name is Sergey Vasin, and I'd like to present you our report on the topic installation and modes of production of polymer fibers with carbon nanotubes by electrospinning. As you know, the addition of even a small amount of carbon nanotubes to a polymer matrix strongly changes the functional properties of polymer structures, and these changes depend on the orientation of carbon nanotubes in the polymer. A number of methods are used to control the orientation of carbon nanotubes in a polymer matrix, such as self-assembly, the Langmuir-Blodgett method, exposure to an electric or and a magnetic field, and one of these methods, the electrospinning method, consists in obtaining thin nanocomposite fibers as a result of the action of electrostatic force on a jet of solution. This method can be used to produce fibers with a diameter of 5 to 800 nanometers, and materials based on such fibers are used in biosensors, nanophotonic, colloidal lithography, and as a porous membranes. To test the possibility of obtaining thin fibers with carbon nanotubes, an experimental setup was assembled. The installation contains a replaceable solid or composite cylindrical collector with a diameter of 80 millimeters, rotated by a motor at a speed of 30 to 2000 revolutions per minute. The polymer solution is supplied by a dosing device from a syringe with a capacity of 2 to 30 millimeters per hour, with an adjustable feed rate from 0.01 to 100 millimeters per hour. The voltage between the tip of the syringe needle and the collector is set by power supply with an output voltage of 2 to 28 kilovolts. In all experiments, a 23G medical needle was used. The solid manifold is made of polished stainless steel tube. The composite collector is a drum of two discs connected by a shaft to each other. There are 0.5 mm deep recesses along the outer edge of the discs. Between the discs, stainless steel conductor with a diameter of 0.5 mm are placed in these recesses. The distances from the tip of the needle to the surface of the collector is changed by moving the dosing device, and was selected in the process of research based on the condition of stability of a polymer dispersion process. Based on this condition, the collector rotation speed was also selected. Modes of fiber formation from pure polyvinyl alcohol. The installation was tested on an aqueous solution of polyvinyl alcohol. One of his first tasks was to determine at what polyvinyl alcohol water ratio the fiber formation occurs. The experiment showed that stable fiber formation was observed at polyvinyl alcohol concentration in the solution of more than 40% at a voltage of 12 kilovolts. With a decrease in the proportion of polyvinyl alcohol in the solution, fiber zinc starting voltage increase, and at 18% polyvinyl alcohol it's already 28 kilovolts. At a polyvinyl alcohol concentration of 11% and a voltage of 28 kilovolts, for fiberization it's necessary to reduce the distance from the tip to the needle to the collector to 130 millimeters. At polyvinyl alcohol concentration less than 11%, fiberization not observed. In the range of polyvinyl alcohol concentration from 10% to 9, instead of fibers, microspheres are formed on the collector. The diameter of the fibers when spraying 40% polyvinyl alcohol solution at the rate of 5 millimeters per hour at a voltage of 28 kilovolts is 3-4 micrometers. And the fiber diameter practically did not change when the voltage changed. When spraying 15% polyvinyl alcohol solution at the rate of 1.2 millimeters per hour and a voltage of 28 kilovolts, the fiber diameter was 0.6 to 1 micrometers. The obtained results of electrospinning of an aqueous solution of polyvinyl alcohol are summarized in table. Similar tests were carried out for polyvinyl alcohol in a mixture with multi-volt carbon nanotubes. When 1% of unfunctional acid multi-volt carbon nanotubes was added to a 40% aqueous solution of polyvinyl alcohol, a continuous layer of nanocomposite without a formation of fibers were formed on the collector. The solution was split not into fiber but into micro droplets, which reached the continuous collector in a liquid state and spread over its surface. The addition of 0.5% of functionalized multi-volt carbon nanotubes to a 40% solution leads to fiberization at a voltage of 25 kilovolts. In this case, the spray rate was only 0.04 millimeters per hour. The thickness of the formed fiber was approximately 0.7, 1.2 micrometers. The obtained results of electrospinning of an aqueous solution of polyvinyl alcohol with an addition of multi-volt carbon nanotubes are summarized in a table. When operating with a solid collector, polymer fiber orientation is not observed because the fiber length is much greater than the collector's circumference. In addition, a solid collector is characterized by an appearance of airflow, which carried away a significant part of the material past the collector. For a composite collector, no airflows are generated and fiber orientation is observed. The film material formed on a composite collector has two areas with different structures. The area above the collector conductor and the area between the conductors. In the area above the conductors, there is a chaotic layering in fibers similar to a solid collector. In the area between the conductors, the orientation of fibers is perpendicular to the conductors. This is due to the fact that a single fiber is caught in the area above a conductor and forms a chaotic layering. A small of the fiber is deposited above the conductor, and the long part of the fiber is pulled perpendicular to the fiber as a result of a rotation of a drum settling between the conductors. Thus, oriented polymer fibers are formed, including those with multi-wall carbon nanotubes. Thank you for watching.